And welcome back, everybody. So this is our fourth lecture in this course, and this is on steady flow to unconfined wells. So last time we saw on the top left here the flow to a confined aquifer. So again, the confined aquifer has water depth that doesn't change because it is confined between two impervious layers, so there is no dropping water. Water is always there, and what we drop is the potentiometric, the head basically. For an unconfined case illustrated here at the bottom, and again this is from Feather, when we pump water in an unconfined aquifer that is in, again, unconfined means it's in contact with the atmosphere, so there's actually a water table, there's actually a water that you can touch if you dig. When you pump that water, actually the whole water table drops, right? So the head is the water table, basically. Again, remember from our previous course. So when you drop the water table, right, there's an interaction here where the depth of the aquifer itself is not a constant in that, cylinder, that sleeve here, basically, again, the area that we're pumping, right, where the water is rushing in from all sides. This area changes basically as you pump, because as your water drops, then the depth of the aquifer is different, so the area where you're pumping into is different, so everything is nonlinear now, so it's a little bit more complicated. So these are the same topics we discussed over and over in our previous course, where you have those squares staying in those equations. Okay, so if we do this now, let's call the head, or the water depth, let's call it B again, but now B is a variable, not a constant, right? So Q is still 2 pi r B, K, and then the change in B over R, but now notice that B here and B here, the variable is the same, outside and inside, so this is a different equation, basically. It's not a constant. We can't just leave B in the constant, so now we have to account for it. So if we separate the variables, right, now B is actually a variable, so it has to, it's not in the constants anymore, it's on its own little side there, right? And so when we integrate this, obviously, when we put the integrals, we still have that log normal on the right-hand side for the 1 over r, just like before. But now on the left-hand side, notice that b, if we integrate b, now we have some b squares showing up. So the answer, or the final equation for, again, the steady state, unconfined, the steady flow to an unconfined well, is that on the left-hand side, instead of the transmissivity, you only have the hydraulic conductivity here, K, right? Because now, again, B is the variable and it's here in B squares. So this is, this is a slightly different equation from before. It's similar, but different. And again, that's because B is now a variable. So you have to keep track of it. Now, if we want to, we can solve basically for here, now I call B is H, basically is the same here. So if we do like before for the radius of influence, right? So again, remember the radius of influence, that R, big R, is, the radius at which there's no influence from the well. So basically there's no, drop of water, basically. So we can say that the head squared as a function of R, distance, equals the head at the radius of influence squared minus, this business. So this is just reshuffling this equation here. But now we have an expression where we can calculate, the edge squared as a function of distance from the well, radial distance. If we, again, introduce or remind ourselves that the drawdown, right, S, the little drawdown, which is the difference, so we can write that H equals the head at the radius of influence minus the drawdown, right? So that's by definition. By definition, this is always true. So now we can introduce the notion of corrected drawdown. So this is specific to unconfined aquifers again. But if we replace basically in the equation H by HR minus S, right, in this previous equation, the Dupuy equation in radial coordinates. So we replace in, and then we can find that this is the whole expression, so we can call this whole S minus S squared over 2HR. Again, this is a variable, this is a constant, and we can call this whole term a corrected drawdown, right? So this gives us just an easier equation to deal with, basically, because now we have, again, KHR, so this is basically your transmissivity, quote unquote, you know, if there is no pumping, right? So if everything is stable, now you can see that K is a constant, HR is a constant, so that's your stable level, if you will, in the well. The radius of influence is also a constant. And now we have an expression that looks exactly like the team equation or theme equation. Sorry, I don't know how to pronounce this name. I mean, I've looked over and over, and different people say it differently. So typically I'll say theme, I think. So the theme equation here from the confined case in the last lecture, right? Now we have an expression that is very similar or basically exactly the same, except now it's a corrected drawdown here on the left-hand side, and this is, you know, the stable level, the HR here at the bottom instead of B, which is constant for the confined case, but very similar expression. And you can also write it as just S, right? The drawdown at any point is this expression. So you have easier equations to use, basically, than the complete form, than this form here. Or things that just look like confined case, you know, equations if you transform them a little bit. Okay, so again, a quick example to wrap this up. So let's say we have 2 observation wells, again, at 3 and 8 meters from the well in an unconfined aquifer, of course. We have the flow rate, we have the depth of the water in the first and second well, respectively. So the depth to the water, right? So now we're looking at the drawdown, basically, in those observation wells, not the depth of water from a datum, right? So this is really important. Again, pay attention to that, because that's where students get confused typically between, is it, you know, the water surface from the soil surface to the water surface, or is it from the water surface to the datum, to the bottom of the aquifer, right, which is the head. So if you're given the head, this is the water column from the bottom of the aquifer to the surface of the water. If you're given the distance from the soil or from the ground surface to the water, this is a drawdown, okay? So always, you know, pay very close attention, because of course those two things are very different numbers. So if the depth of the aquifer is 10 meters, what is the hydraulic conductivity? And again, you can just use this equation that we just derived in the previous slides, replace everything by their values. So here Q equals 500 liters per minute. So now I convert that to seconds. And then to, to hours, and then to days. So this is, 500 liters per minute. So times 60 minutes per hour times 24 hours per day. So now we have liters per day divided by 1,000, which is now in cubic meters per day, which is typically, you know, what you want. Divided by pi, and then 8 squared minus 5 squared. Again, the reason is because it's 10 meters minus 2, right? So 10 minus 2 equals 8 meters. And then 10 minus 5 equals 5 meters. So these are the actual heads, right? So now we have the heads, so we place those in, b squared minus b1 squared, and then the log of r2 over r1, so 8 and 3 meters right here. Okay, and then the answer is 5.76 meters per day. That's the hydraulic conductivity of the formation that you're pumping into, of the sand, or whatever it is. Again, remember, meters per day is usually a good approximation for hydraulic conductivity in sandy formation. Okay, I think, oh, excuse me, this is not it. Actually, I have one more slide with the problem with a source, right? So remember in our previous course when we did like the pipe drainage problems, for example, or, you know, something with a recharge, basically if you have rain on the land, now we have a recharge to the aquifer, and that changes the makeup of that problem. So what happens if you have rain now, right? So if you have a source. So again, you take the same mass balance equation. So you have the 2 pi r, and this is the equation we had, you know, before. So 2 pi rb is that sleeve area around the well, and this is where the water flows into the well. Now think that for the recharge part, right, the area around the well that the water is coming into is actually you know, a circle on the surface here, right? So it's actually pi r squared, right? Pi r squared is really the pi r squared is the area where this water is coming in, because it's coming from the sky down around the well. So it's really the circle, you know, at the top. So pi r squared. So now we have pi r squared here, and then we eliminate that 2 from the 2 pi r on the, for the other thing. So now we have pi r squared times W is really the, you know, the amount of water going into that. Again, this is pi r squared times W basically. Okay, so this is the circle up top. So this is, again, important to remember where is the water coming in. So if you have now recharge from rain, this is what you want to do. Okay, we will do some little example problems in your homeworks. Thank you very much, and I'll see you in the next video where I'll show you some finite difference tricks and how we do this basically in Excel, how we represent those equations for the confined and unconfined cases in a simple aquifer with finite differences. Thank you.